right, so we are going to be talking now this unit about our electrons, okay? And so our electrons, oftentimes what we're going to use is the Bohr planetary model of the atom. So if we remember, right, Bohr came up with a model where he's got the nucleus of the atom and then our electrons that are traveling around in orbits, okay? So we're going to use this model for a few pieces through this next unit, okay? So we have a nucleus and we have orbits. All right, so what experiment did he do? If we remember, right, Rutherford had identified that an atom has a nucleus, but he didn't really look at where the electrons were. So what Bohr did was he came in and he used emission spectra, okay? And so what he did is he ran electricity through some elements. And when he did this, he saw that there was light that was emitted. So he observed the colors of that light. All right, and so what he saw was that those lines, or that the light that was being given off, were very distinct energy, or distinct lines, right? Really distinct lines. And so those distinct lines, he interpreted it as meaning that the electrons weren't just moving willy-nilly about, they actually could only be in specific quantized energy levels, okay? So the distinct lines, distinct, mean that the electrons have to be in specific quantized energy levels. Okay? So we need to know a little bit about our types of light to really understand the Bohr model, right? So the electromagnetic spectrum is really just the range of frequencies of electromagnetic radiation. So EM, electromagnetic radiation. Radiation. So our properties of light, what we need to know is that we have kind of this wave-particle duality, okay? This is why we're able to kind of release the energy off from our electrons without really giving up much, okay? Because it's kind of a wave, okay? So we have our electromagnetic spectrum below. What we can see is that really we go from cosmic rays all the way down to really low wavelengths, long wavelength broadcast waves. So we've talked about our gamma rays, right? These are getting released from our nuclei when they undergo gamma radiation, right? But we have a lot of other rays in here, right? A lot of other wavelengths that can influence and can interact with our molecules, okay? And one of the big ways that it interacts with it is actually in the visible light spectrum, okay? So on our visible light spectrum, we have red with relatively long wavelengths, right? This would be our 700 nanometers down here. Our 600 nanometers, we've now kind of moved into the orange and yellow colors. Down to 500, we're now green. And then our 400, this is going to be our violet and our blue. Okay? So as we decrease our wavelength to shorter and shorter wavelengths, right, really what we're doing is we're going to be increasing the amount of energy that gets transferred. Okay? So our shorter wavelengths have higher energy, and our longer wavelengths have lower energy. And that's going to change how it interacts with our molecules, okay? Okay, so now let's look back at our Bohr model, right? Our Bohr model, what we have is we have a nucleus in the center, and then we have these orbits, okay? So our electrons are going to be absorbing or releasing energy based on the light, okay? So what we need to do is we need to identify whether they've gained or released energy. To do that, we look at the ground state versus the excited state, okay? So for neon, we know that neon as a normal atom, right, an uncharged atom, would have 10 electrons. So 2 of those electrons are going to go into the first energy level. That's why we have a 2 here. And then 8 of our electrons are going to go into the second energy level. So our first energy level can always only hold 2 electrons. Our second energy level, this one can only hold 8 electrons. So our ground state for neon has the first energy level full with 2 electrons, and our second energy full with 8 electrons. But if one of those electrons were to absorb some energy, it could become excited and jump up into the third energy level. So now what we see on the right-hand side here is that there are 2 electrons in the first energy level, so there's our 2, but there's only 7, 1, 2, 3, 4, 5, 6, 7, that are in the second energy level. That 8th electron jumped from the second energy level up to the third. So now this is an excited state, okay? So 2, 7, 1, 2, 7, and then 1 in the third energy level tells us that this neon atom is excited. It has absorbed some energy, okay? So we need to be able to identify our ground state versus our excited state, right? So our ground state configuration for lithium here, if we look at lithium, lithium would have 3 electrons, so our ground state would be 2-1, okay? The excited state for lithium, we have lots and lots of options, but we still only need 3 electrons. So we could have 1-2, where one of the electrons from the first energy level has jumped up into the second, or we could have 1-1-1, where it's jumped up into the third energy level, or we could have 2-0-1. Now that electron that was in the second energy level has jumped up into the third, okay? So the ground state, our lowest energy levels are filled. For the excited state, really it's saying that the lowest energy levels aren't filled, okay? Okay, so then down below we've got a bunch of practice for you. What we have, again, what we need to know is that the first energy level can only have 2 electrons. The second energy level can only have 8. I'll put this down at the bottom. So first, we're going to have 2 electrons. The second energy level can have 8 electrons. The third energy level really can hold up to 18 electrons. But, right, we always say that we make a rule and then we break it. We can hold up to 18 electrons, but oftentimes we'll fill 8 electrons. Whoops, that's not clear. We'll fill 8 electrons and then go to the fourth energy level and fill 2. And we'll talk about that later on and why that is. So our fourth energy level, this one we can hold up to, what's 18 plus 14? I think that's 32 electrons that we can get in there. It's again got another rule kind of like this. Whoops, There we go. It's got another rule kind of like this, but we'll deal with that later, and we'll talk about it later. Okay? That's all for now.